In this video, I will present the workflow for discriminant validity analysis. This workflow is based on my paper with Joe in organizational research methods, and we analyzed discriminant validity, different techniques, and then we proposed new principles on how to assess discriminant validity. Some of the key things that we want to emphasize in the paper that discriminant validity is not something that you test for and you either have or don't have. Instead, any potential discriminant validity issue can come at different degrees. So it's not a yes or no, but it is rather a continuous problem. So you can have no problem, mild problem, severe problem, and that kind of things. Instead of just saying that certain statistic exceeded the threshold, we have no problems, and then proceed interpreting your results as if the problem did not exist. Each of these levels that we have in the paper also imply different consequences for the research and different actions for the researchers. So discriminant validity is not something that you declare that you have and then proceed. It is something that you assess the degree of and then you act on based on those assessments. So we have two objectives. For each correlation pair in our study, we need to determine the level of a discriminant validity problem for that correlation pair. That's the first objective, and then we need to deal with the problem based on the level. We propose also two different statistics two different statistical approaches for implementing this workflow. These are CI-CFA SYS, and CI stands for confidence interval, CFA stands for confirmatory factor analysis, and SYS just refers to system because this is a more systematic approach than simply running an analysis and reporting the results. Then chi-square SYS refers to the same technique, but instead of looking at confidence intervals, we determine levels based on nested model tests. Which one of these is better? The chi-square variant is slightly better statistically according to our study. So it has slightly more power, but the difference is very small. This confidence interval based assessment is a lot easier to apply, and it's a lot more difficult to apply incorrectly. So this chi-square test and nested model comparisons are very easy to misapply by scaling your latent variables incorrectly or forgetting to switch from first indicator scaling to factor variance scaling. So because of these reasons, the practicality of the confidence interval based assessment and the fact that it's less likely to be misused, this is our recommended alternative. Let's take a look at how you apply these workflows. So the first thing that we have in the workflow is that we need to start from the definition which I reproduce here. The important thing in the definition is that we need to determine what correlation is low enough to be considered not a problem. And that probably depends a lot on the context. So we propose that correlation below 0.8 are probably unproblematic in most cases, but that is not the general rule. For example, gender, identity, and biological sex correlate at 0.99, and sometimes that kind of correlations happen, and we just have to live with those. And it will be difficult to say that sex and gender identity are the same, even though they're almost perfectly correlated. We just need very high quality measurement, large samples, and we can study things that are even this much correlated. Also, the workflow does not apply to continuum constructs. For example, if there were two scales, happiness and sadness, that we could consider to be two opposite poles of the construct of mood, then this workflow would not apply. So we need to define what is low enough, and we propose 0.8 as a conservative starting point. Of course, if you have good reasons to use other cutoffs, then justify your reasons and go ahead and use other cutoffs. Then we estimate a confirmatory factor analysis model and inspect the confidence intervals of the correlations. We recommend that this is done by fixing the factor variances to be ones instead of scaling the factors by fixing the first loadings. Alternatively, you can simply just request standardized estimates from the statistical software and inspect the confidence intervals based on the standardized estimates. And then you determine a class for each correlation by looking at the upper limit of a confidence interval, or if it's a negative correlation, then you look at the lower limit. And if the upper limit exceeds 1, the perfect correlation, then you always have a severe problem. Then you can't say that two scales or two factors are empirically distinct at all. Then you have varying levels of problem determined on where in your classification the upper limit falls into. And based on those correlations, these classes, we then deal with the problems. The workflow for the chi-square test is a bit more complicated. It starts with the same thing. So you need to determine what is low enough to come up with the thresholds, and then you estimate the same confirmatory factor analysis, which gives you the correlation. So you fix the factor variance to be 1s instead of fixing the first loadings to scale the model. Then we determine an initial level for each correlation based on the correlation estimate. So for example, if a correlation estimate is 0.8 and we use this classification here, we would position that correlation on the marginal problem level. Then we would test that correlation against the next level. So we would take the lower limit of the next level, which is 0.9, and we constrain the focal correlation to 0.9. We re-estimate the model, and then we compare the original model and the constraint model. If they are not statistically significant, then we move that correlation to the higher level. So in this case, we would move the correlation from marginal problem to moderate problem. Then we go and we test the next level. So we know that now that the correlation is at least a moderate level problem, we would test against the cutoff of 1, which is the cutoff for severe problem. And if we find that the model where the correlation is constrained to be 1 fits worse than the unconstrained model, then we conclude that the correct level for that correlation would be a moderate problem. So it is originally in the marginal problem, but it's not statistically significant from the moderate problem, but it is significantly different from a severe problem. Therefore, the correlation belongs into the moderate problem. We do this for every correlation, so it requires some effort to do all the model comparisons, but it can be automated, which is a good thing. Now, after we have established the level for each correlation, for each factor, or for each scale pair, we need to determine what to do about the problems. What if we find problems? Well, we are looking at two different things. We need to first, the easy case, if there's a correlation with no problems, we don't need to do anything. For any other correlations that belong to the severe problem, moderate problem, or marginal problem class, we need to determine what is the source of the problem and what is the magnitude of the problem. And then based on that, we might need to do something. Let's take a look at what actions the different levels imply. As I said, if there is a no problem class, then that implies no actions. If all the correlations that you have in the study fall into the no problem class, then you can simply declare that you implemented the CI, CFI, SUS approach, and you detected no problems, and that's your discriminant validity analysis. If you find problems, then you need to deal with it. The easiest case is the severe problem. So in the severe problem, you cannot rule out the null hypothesis that the two factors are perfectly correlated in the population. And in this case, they are not distinct at all. And if that happens, then we need to rethink the conceptual definition, measurement, research design, or all of this. So that indicates a problem that basically blocks your progress with your study before the problem is solved. These other cases, the moderate case and the marginal case, are something that we can live with. In the marginal case, there is a problem, but it's probably safe to proceed without doing much. Of course, you need to explain that you have a marginal discriminant validity problem, and then you need to explain why you think that it is not a problem in your particular study. If you have a moderate case, which in our example is a correlation of more than 0.9, then we need more evidence. So in moderate cases, you also need to demonstrate that it's actually not a systematic problem with the scale. If everyone uses a scale of two scales to measure two constructs and always gets this moderate problem or severe problem, then we know that there is something problematic either with the concepts or with the scales, and we need to do something. So if you have a moderate problem, then you need to look at what kind of discriminant validity evidence prior studies that have studied those scale pairs have presented, and then make a justified decision on what to do based on the prior evidence. So this is a lot more serious than simply a marginal case. So this is the what to do based on the severity. But in addition to severity, we need to consider what is the source of the problem. Why is the reason that there's a high correlation? And we can think of three different reasons for there to be a high correlation between two factors. The first is that really there is conceptual redundancy. So the two concepts that we are studying are actually the same. And this is a scenario that has been addressed in prior research. For example, Schaffer's paper presents a nice set of guidelines on how to do conceptual analysis. Podsakov's paper presents a nice set of guidelines how to do conceptual analysis. So you can follow the guidance in those papers on how to make sure that the concepts that you're working with are actually distinct and not simply different labels for the same thing. Also, Krause's article presents interesting observations with this regard. So look at the conceptual side first. Then the second thing that you can do is to inspect your measurement model. If the assumptions of your confirmatory factor analysis fail, so the model does not fit the data well, that can cause a correlation to be very high. So it is possible that there is no conceptual problem, but you have, for example, a cross-loading or a double-barreled item that is not properly modeled with a cross-loading that causes one of the correlations to shoot up. And that kind of problems need to be detected. I have another set of videos where I explain how to do confirmatory factor analysis diagnostics. So if you don't know those, then you can search for that in the video library. Finally, it's possible that it is a data problem, particularly if you have a small sample. So let's consider an example of we want to study hair color and gender and their effect on, for example, hireability of a person. And we are studying only blonde men and dark-haired women. So we cannot say which one is the cause of employability, whether it's the gender or the hair color, because the gender and hair color are perfectly correlated in the sample. And this could happen for two reasons. It could happen because our sample size is so small that by chance we don't get any blonde women or dark-haired men, or it could be because we have a systematic error in our sampling strategy. So a high correlation can be also not only evidence of conceptual redundancy, measurement problem, but it can be a sampling problem. So we need to consider that as well, and then maybe either collect more data if we decide that it's a small sample issue, or we need to reconsider our sampling strategy if we realize that we actually did not sample all the relevant units that we would like to include in our study. So in a summary, these two workflows, how they work: you first start by choosing context-specific cutoffs if possible. The 0.8, 0.91 cutoffs that we have present here are not any golden rules that should be always followed, but you can use other cutoffs depending on your context. Then classify each correlation based on the cutoff. Our example uses no problem less than 0.8, marginal problem 0.8 to 0.9, moderate problem 0.9 to 1, severe problem not different from 1. Based on those correlations, identify the sources. Conceptual overlap, measurement problem, and sampling problem are the three possible causes for a high correlation. And after that, decide what to do based on the severity of the problem. So if you have severe problems, then you simply can't proceed using the correlations. you need to do something about the problem. With moderate problems and marginal problems, it is possible to proceed with the study, but with moderate problems, you need to present additional evidence to make sure that there is no systematic problem with the scales or concepts that you're studying.